So, hi everyone. So, today I'll be presenting this paper, ZegCLIP, which is published in CVPR 2023. There they use a clip and zero-shot learning together for semantic segmentation. So, these are the contents of today's presentation. So, this paper is heavily dependent on clip. So, I'll do a quick recap on clip. I have presented clip weeks back, so it has been quite some time. So, I'll give the quick recap. Then I'll talk about the uh, just a second. Then I'll talk about what is zero-shot segmentation problem setting, like how it's different than the normal segmentation. Then in this paper, they have proposed some baseline. From that baseline, they went uh, further and proposed further things. So I'll first explain the baseline and then I'll go deep into the paper. Then I'll talk about the main contribution of the paper. Like they have three main contribution basically: the tuned clip transformer with prompt tuning method, and for training they introduced a new loss function, this one, the non-mutually exclusive loss. And for uh, zero shot segmentation property, they use this relationship descriptor to keep clip zero-shot property intact even while training in supervised learning patient. Then and finally, I'll show the experiment results to see the effectiveness of this method. So clip was first introduced in this paper from OpenAI, and this is the model apparently. So in clip, we have two encoders. One is text encoders and an image encoders. Let's say we have n number of image, and we have n number of uh, text associated with the image, then we will have n number of image embeddings from the image encoder and n number of text embedding from text encoder. In clip, they take the dot product of both image embedding and text embedding and make a matrix like this. And so here, these diagonals are the associated points for each inputs. So for image one, this is the one. For image two, this is the one. So they train clip in a way that they maximize this diagonal of this matrix. So when they train clip in that way, what happens is the image encoder gets some text information. Image encoder basically learns to describe how to associate some text with that image, or how some text is related to that particular image. And text encoder also learns like same thing, like how some certain text is related to certain image. So what happens is what they say, if the batch size, if let's say n is the number of batch, if n is large enough and it is trained in a large enough data set, the image encoder and text encoder will be generalized enough to explain any scene in the world. So if that is the case, we can use one good property of clip. So we can just take any image or any number of text input together and classify one image like this. Like we take an image and a certain number of input for text encoder, and the highest value in the output, like this output, like let's say these are the outputs, like multiplication of I1 and T1, and T1, T2, and T1, I2, and so on. The maximum value of this vector would be the correct association for that certain image. So clip is very good in classifying unseen image because it was trained on in whole internet practically, and of course on OpenAI. So they have infinite resources to train it on everything. So it has a really good property for classifying images in most of the cases. So normally in these days, the researchers are going on how to use CLIP in multiple downstream tasks, not just uh, image classification. They have been using it for like segmentation and so many other tasks. So let's see what is this paper's problem setting. So in traditional segmentation methods, the normal objective is to classify individual pixels within the given classes in the training. So let's say we have three classes like cat, human, and dog. So in normal segmentation settings, all three classes will be given, and the model will have to learn how to classify the images in between those three classes. But in zero-shot segmentation settings, there will be some classes which are not seen in a example. Let's say we have three uh, classes for our dataset, like cat, dog, and human. There might not be human in the dataset in the training. So, but the model is supposed to classify or segment also human who are in testing. So this is problem setting for zero-shot learning to classify the unseen data. Zero-shot segmentation setting has uh, basically two types. First one is inductive zero-shot setting. Here, both unseen class names and images are not accessible to training. So here, let's say human is the unseen class in the setting. So the human class name and the image, even in the images of human in any image in the training will not be available. But in other setting, transductive zero-shot setting, there might not be the class name. So the human class might not be implicitly there, and but there will be humans image with other classes. Let's say there will be a dog and a human together in certain image, but that human would not be annotated for that training. And that's the other zero-shot setting, zero-shot segmentation setting. So what are the previous approaches using CLIP in zero-shot segmentations? So most of the previous approaches had two encoders for segmentation. One is a class agnostic generator to generate something, and then they use that generated image for embedding for CLIP input and use CLIP to do the segmentation. But problem here is they use two image encoder, and since they use a transformer and two image encoders, it gets really slow. So in this paper, they try to incorporate all the features of CLIP and zero-shot segmentation together with one one image encoder, which makes it substantially faster than previous methods. Yeah. So this is the overall architecture. I'll come back to it again at the end. It seems quite complicated in the first glance. So if I just give it a like high-level overview, there will be text input and image input, and for classification individual pixel, the uh, divide the image into patches. Like here we can see the patches, and they use CLIP to do like certain things, which we'll discuss later, uh, to do the segmentation. Like I'll come back to it later again. So the baseline. So to start the baseline, they started with a vanilla Lighto transformer, which treats semantic segmentation as a matching problem between representative class query and image patch features. So, like as I said earlier, they divided the image into patches, and they were querying the specific classes for each patches. That was the baseline here. So to like formulate mathematically, here T will be the text encoder and phi would be a linear projector. So we will have the query from the text, and the H is the patches of the image, and there will be one linear projector which will get the keys from the patches, and the value would be from another linear projector, which you'll be getting from the patching. From the patching, would be getting the masks using this equation. So, and from the masks, so we can see we'll have C by n dimensional matrix. The C is the number of classes available in certain data set, and n is number of patches. So if we just take the argmax for each patch, we will get the correct segmentation for each pixel. And if you combine all the patches together, we can get the segmentation for whole image. But the problem with this naive approach is another thing actually I didn't mention. So for the patches, they used two approaches in baseline. They first fixed the number of patches. Initially, there was one experiment with that, and there was another experiment where they used some network to make the patches and feed into the transformer, feed into the image encoder. So the result is shown here. So this one here, they fixed the number of patch in the image, and here they use some convolutional network for the patching, for the patches. So what the problem is, like when the model is trained on this baseline model, it performs relatively well in the scene training classes. So the scene training classes, as I explained earlier, it's available in the training set, but it struggles in the unseen classes. So the purpose of the whole thing classes, but it's struggles in this case in the fixed patches case and both non-fixed patches case in unseen classes. So to solve this problem, I'll come back to this part again later. So to solve this problem, they have proposed these three proposal to mitigate the issue of overfitting into training classes. So what is deep prompt tuning? So the CLIP originally had the zero-shot compatibility. So we have seen earlier as CLIP, as is mentioned in the previous paper, CLIP can generalize almost all the scenes in the world. So CLIP is already generalized for almost all the scenes in the world. So their next approach was to keep the property of CLIP while it can also be fine-tuned for any specific data set. So for that, they used one transfer learning method called prompt tuning. In that method, they add layers in between CLIP layers. So these are the CLIP layers, VIP P16. These are the CLIP layers, layer 1, layer 2, layer 1, 2, whatever. So they add some layers or some learnable parameters within the in between the layers of CLIP, where the CLIP, these ones are the frozen, these ones are the frozen, which will keep the property of CLIP intact, but there are some learnable parameters. These are the learnable parameters which will learn dataset specific things. So let's say if it was trained on COCO dataset, it will get these parameters will get the property of COCO, but these ones will be frozen, so it will still be generalized enough to do zero-shot segmentation. So in this approach, it, it it also improves some accuracy. So we can see previously the unseen classes accuracy was 16.3 and 13.8, but using the deep prompt tuning, we got 28.3, so it improved accuracy a bit. Then the next one, they proposed another loss function. The reason behind proposing this loss function is in normal, let's talk about a normal segmentation set. So in normal segmentation settings or normal any classification settings, when you have multiple classes, we can just use softmax and be done with it. It works normally perfectly fine. But in softmax, one primary assumption is all the classes would be mutually exclusive. So what that means is the given number of classes in training would be the only classes in testing too. So if the model is optimized in a way, it will not assume anything other than any other classes other than the classes given in the training set. So, but in the zero-shot segmentation setting, we want to also segment the classes which are not available in the training set. So to solve this issue, this they're prescribed to not use softmax. Without using softmax, they propose to use binary cross entropy and sigmod for individual classes. So let's say for human, there will be two things. Is it a human or not? For dogs, there will be two things. Is it a dog or not? It will not be classifying everything. It will just classify just one thing. So it will not lose all the, but what I meant to say is like it will not be prone to, it will not be just choosing the classes given in the training set, but it will also be choosing, it might also choose the classes from outside the training set. So along with BCE loss, they also used focal loss and dice loss for segmentation. So using this non-mutual exclusive loss, they also improved some accuracy here. So combining with GPT and NEL, they reached to 40.4 compared to 28.3. And for the last one, the relationship descriptor. Okay. So normally here, in the baseline, they just do the text embedding from the text encoder and image embedding from image encoder and the patches from the image together and put it in a text patch matching decoder and got the final segmentation output. But the problem here is also it also gets overfitted to the training classes since there is no specific like we use again softmax. Like here you use softmax. So if there is not softmax, as I will explain earlier, softmax prone to just choose classes which are only given in training set. So it just gets like, overfitted to the training set and performs worse in testing set when the classes are not given in the training set. So to solve this, they took one property from CLIP, as I have like mentioned earlier, that in CLIP they take the dot product of image embedding and text embedding together and trying to maximize the diagonal to get the zero-shot property incorporated in them. So they motivating from there, they in their experiment they found if they use this equation here for relationship description between text and image, they get much better result. There's a problem of uh, not classifying properly the unseen classes, uh, noticeably limited. So here R is, so yeah, let's start from here. So T is here the text embedding, G is here the image embedding. So R is the combination of both, like it's given here. So, and this one is the Hadamard product of both, and the concatenate both and get the final relationship descriptor and input it into this text patch matching decoder. So that improves the accuracy significantly, I guess shown here. So it improves the accuracy to 77.8 from 40.4. So to summarize, so here we have that patches of an image. We input the patches to the image encoder, and the image encoder will have some deep prompt tuning, which basically means it will have some layers in between the frozen clip layers, which will help the model to be more fine-tuned to one particular data set or particular classes in the data set. And this is the clip text encoder, so which will get the text and get the text encoding. Then from the image encoder, we'll get the embedding for it, the each patches, like for each patch you'll get some embedding, and from class embedding and this here there will be, oh, so another thing, we'll get some token as a value from mission coder 2. So using that token, we get the relationship descriptor together, and using this relationship encoder and the patch embedding together, we can finally get the segmentation result. So yeah, so these are the experiment results uh, for this method. They have done experiment for in Pascal VOC 2012 dataset and Coco Stuff 164K and Pascal context dataset. So as they're showing here, they are current state of the art for zero-shot segmentation methods. And here they, remember earlier we have talked about inductive methods and transduct, uh, transductive method. In the inductive method, there is no mention of uh, any unseen classes, but in transductive method, there might not be any mention of class names of any unseen classes, but there might be images. So in this one, the accuracy is a bit low compared to this one, because it has seen the images before, so the accuracy is a bit higher. And overall, it performs better than all the other existing zero-shot segmentation methods. And for inference, since they're using just one encoder, it performs noticeably better than other zero-shot segmentation methods. Like here, ZegFormer is 1.7 FPS in VOC dataset, but it's 9 FPS in ZegCLIP. And in Coco, the other one is 1.5 and the clip is 6.7. So it's noticeably faster than the previous methods. Yeah, so that was it for me. Thank you for listening.